All right, guys, this is the last unit for this course on confidence intervals for linear regression. So basically, the whole idea with this is that we've looked at linear regression before. We've used our calculators to come up with the lines of best fit. Um, but if you think about it, that's only one specific point. It's like a point estimate for that line, and we can have instead of looking at just one specific line, we can look at a range of values that the line could take on that makes sense, and so we can have like an interval for that for our lines. It's kind of the idea behind this is that we can kind of come up with a bunch of different equations that could that are plausible for data sets. That's kind of the idea behind this. So if you look at this, when conditions for inference about the slope are met, sampling distribution of the slope will be approximately normal, with the mean of beta being your slope, and the standard deviation being sigma over sigma x root n. So what factors affect the standard deviation of the sampling distribution of the sample slope? What if we don't know the true standard deviations? So here I'm start writing some stuff down. So here I talk about sigma. Okay, since sigma is in the numerator, so when the standard deviation is large, and this is large, then the whole right side of the equation will be large. Right? If I have a big thing in the numerator up here, right, this whole fraction is going to become really, really big. Okay, and so what that means is then you have larger variability. Okay. Now take a look at what's in the denominator. If sigma sub x and n are both large, and well, then think about what's going to happen then. If your denominator, if you have a really big number in the denominator, you have a really big number down here, that's going to make this whole fraction really small, and therefore you're going to have less variability. So then sigma, the standard deviation of the slopes, so sigma underscore b, will become smaller. This leads to more precision. And sigma sigma sub x down here, okay, that is your standard deviation of your x's. Your sigma underscore b we use those subscripts just to kind of help us separate what standard deviations we're talking about. So mu b right here is the mean of the slopes. Okay, sigma b is the standard deviation of the slopes. Okay, so that's kind of where those things come from. And so yeah, so basically what we're looking at here is depending on what these are our conditions. This is how you calculate the mean and the standard deviation. Well, depending on what the standard deviations are, you're going to impact what the mean or the standard deviation of the slope is going to be, right? The mean of the slope is just going to be the actual slope. So what if the regression model, when the conditions for inference are met? Talk about a couple things here. So the shape of the distribution. So the distribution b values of betas is unimodal and approximately normal. And so you're like, well, what does this mean? So if I draw this little face, if I draw a little distribution here, okay, right? What we're saying is that the center of this peak is going to be at, this is what your calculator is going to give you. This is your beta, okay? But really, we do have, depending on the sampling that you do, you may have a beta that's here, you may have a beta that's here, right? It's not necessarily always going to be at this one spot. So we end up having this distribution of betas where you have a bunch of different slopes, right? Now the likelihood that your slope's going to be way out here is very small, right? And same thing as the likelihood it's going to be way out here is going to be really big, it's going to be really small. But the likelihood that you're going to be somewhere in this middle section is probably pretty high, right? So what we want to do is give a confidence interval for all these slopes, right? So what could be the range of values that our slopes could take on? It's probably not going to be exactly this B, but it's going to be somewhere near that. That's kind of the idea behind this whole unit is like, okay, well, what is this confidence interval going to be? Okay, so the distribution is approximately normal. You have the center, the mean of beta, and beta is just the variable that we use for slope. Will approach the slope of the true population. Okay, and the spread is the standard deviation of the betas is equal to the equation given up above, right? Is equal to this guy right here. If you meet that 10% condition again. So once you understand what we're trying to do, we've done this all before. We've looked at confidence intervals before, right? It's just now we're looking at it in terms of slopes of lines, which is kind of a weird idea. But this is the idea that, we're not going to actually be at this specific beta. We're going to have a range of values that our slopes could take on, depending on the sampling that we do. Okay, so here we have a little problem here. So we're looking at the regression line for Old Faithful is this, for the standard deviation of this. Assuming that the regression model is valid for eruptions for 4 minutes, how often will we need to wait more than 90 minutes until the next eruption? Okay, so then I can just use this equation and I can plug in 4 into my x. So let x be the length of the eruption. And I can just plug in 4. So $33.35 plus 13.29 times 4. And that's going to give you 86.5. So based on our line, we're going to expect this. Okay. But we want to find the likelihood that you're going to have to wait 90 or more minutes. And like we said above that this is approximately normal, so I can use a z-score. You can go 90 minus 86.5 divided by the standard deviation. Okay, and then find the corresponding p-value from there. That's a good little review. So what are the conditions that we need to check before we actually do this linear, this regression inference? So we need to check that it's linear. Okay, so the actual relationship between x and y needs to be linear. So how do we check that? Check with a scatter plot. Check with residual plot. This is a good chance for you to review on how to do scatter plots and residual plots in your calculators. Those will be pretty helpful. Okay. You need to check normality. So you can, again, do the same thing, make a dot plot. You can do a lot of graphing. Stem and leaf plot. Histogram. Okay. You got to check for equal standard deviations. Okay, so you would want to look at the residuals. Yeah, we've done all these on our calculator before, so that'll be nice. So you can kind of just get a little refresher on those. But look at the residuals. You want the vertical spread of the residuals to be fairly consistent. So we've talked about this before, but what this is saying is that when you look at your residual plot, you're going to have something like this, right? And what you want to see is just kind of like they're all kind of evenly spread out above and below, right? Something like this. This is good, okay? What you don't want to see is a residual plot that looks like as unequal. So it's either going to start really spread out, and then it gets narrower and narrower as you go along, right? Something like this is not what you want to see. The other one being the opposite, where it starts really narrow and then it gets wider and wider as you go along. So if you see something like this, right, and you see we kind of have this spreading of this pattern. This is not what you want to see, right? So those are things that you want to look for. And then last thing you want to check is independence and randomization. So do we have some type of random sampling / assignment? And then our favorite one that we use all the time, n is less than or equal to 1/10 of big N. Okay. So these are all things that we got to check. So we're going to do a lot of graphing in this unit. Really good review. These are, you got to check all these conditions before you decide to do this inference. Okay. So moving on. What are the 3 parameters we need to estimate in a regression model? So what we need to do is we want to know sigma. We will use S to approximate. So we say S is equal to the square root of the sum of the residuals squared sum of the residuals squared over n minus 2. Okay. And we know that B is equal to the slope is an unbiased estimator for the true slope beta, and A is equal to the y-intercept. And this is an unbiased estimator for the population y-intercept, which is alpha. Okay. And so what is the standard error of your betas? How do we calculate this S? So your standard error, this is what we're going to use in our confidence interval, is equal to S divided by Sx times the square root of n minus 1. And this represents spread of the sampling distribution of B. Okay. And so now going back to confidence intervals, remember confidence interval statistic plus or minus your critical value times the standard deviation of the slope. So here, what's the confidence interval? For finding the slope, you're going to have B, because we're trying to estimate our betas. So B plus or minus your T critical times your standard error of your betas. So the nice thing is we're just doing the same thing that we've done before. It's just a matter of kind of switching up the way we're looking at it and what we're looking at. Okay, so here's some output. We've looked at these before. See if you can remember. It's good practice to see if you can find the slope just by reading this output. It's kind of helpful. And see if you can find, see if you can interpret the slope in the y-intercept, and see if you can interpret the standard deviation of the r-squared. This is a really good reminder from back in chapter 2 and chapter 3. So yeah, it's a really good idea. And so we'll look at this problem in class. If you don't remember, that's fine. And we'll do the state plan to conclude. We'll do this whole problem. But this is a good practice. So see if we can do the first couple of parts, and then see if we can attempt part E. If not, we'll do that in class. Go from there. And so now we're just moving to the next part, which is instead of doing a confidence interval, we can also do a significance test. Is the slope of our line significant? So a couple things to look at. So describe the association, right? So this is thinking back to SOX, right? Shape, outlier, center, spread. Remember, the association is positive if X increases, Y increases. Negative if X increases and Y decreases. Again, we got another computer output. See if you can determine the equation of the LSRL. See if you can calculate correlation. Remember, correlation and R squared, they're related to each other. So you can kind of use our R squared value to find correlation. So see if you can remember how to do that. See if you can use this LSRL to calculate some scores. So we see if we can do all those things. It's a good review. Questions. Okay. Explain why it's important to randomly assign. So think back to chapter 4. So this is a lot of good review here. Okay. And again, we'll go through a lot of these questions together. But this is just really good practice. So I'm going to jump to number 10. Okay, because it's kind of where we're getting to some of the newer stuff. So state the hypothesis you want to test and define the parameter. So we can perform significance tests to determine whether a specific value of beta B is plausible, / whether there's an association. And again, remember your null hypothesis is your baseline, so that's your beta equals 0. And then HA is going to be based on your graph. So it's going to be less than, greater than, depending on what your scatter plot shows you. So if you think that the trend is positive, then you say beta is going to be greater than 0. If you're not sure, beta will be not equal to 0. Or if it's a negative correlation, you can say beta, or negative association, you can say beta is less than 0. So kind of just look at the graph. There. Okay. And this beta, if your beta is going to be equal to 0, that's showing you there's no association, right? Because the slope isn't right. One isn't increasing, the other one is, or it isn't decreasing, right? So if you show that your beta is equal to 0, then you can show that there's no association. So that leads directly to the next question, which is what is the evidence for HA? And so if your p-value is less than alpha, we reject HO, and we have evidence for an association. If P is greater than alpha, we fail to reject HO. and we have evidence for an association, because your beta is going to tell you as one thing increases what's happening to the other, right? What's happening to your two variables. So the whole idea is that if we can show that, that a significant or not can tell us if it's going to be, if there's an association between the two variables. And so how do you calculate the test statistic that we want to test, or that we want to use to determine if our p-value is going to be significant or not? Here we have t equals beta minus beta 0 all over SC. Okay, so this is a general equation. And it is on the formula sheet. Okay. And couple things I want you to notice is that beta 0, this is going to be 0, right? That represents no change. Okay. The thing is that we do have to calculate this, so you have to be careful about that. So we'll kind of go into those details in a little bit. And so we'll look at this problem in class together, but see if you can find the standard error and your b value from the output above. See if you can calculate t value. And let me just put in here, degrees of freedom equals n minus 2. Okay. See if you can take a second, see if you can find that, and then see if you can make a conclusion. Again, we'll go through all these problems in detail in class. Okay, so now last couple of things, we might just get the whole video, the whole unit done in one video, which is kind of cool. So can you use a calculator to construct the CI? Yes, but you're still going to do all 4 steps, and we'll look at that together. But here's a good practice problem. We'll do all 4 steps together in class. Again, if you want to take a shot at it, please do. And the last thing that I want to talk about is just transforming data, which can be pretty useful when you start looking at stuff. But basically, the whole idea is that if you have data like the one here on the right, okay, you could do a linear model, right? If I do a linear model, you'll get something like, this, which isn't terrible, okay? But if I was going to draw a line of best fit, and I'm not worried about just being linear or not, right? I would draw some exponential function like this, right? And it's going to keep increasing like this, right? And so what you can do is you could transform your scales on your x and y axis, right? You can do whatever you want to in order to transform and to get something more linear, and then you could do a linear regression. Okay, so that's kind of the idea behind this, is that I can transform either my x's or my y's, typically your y's, in order to get something a little more linear. So here, I'm going to write some stuff. So linear and nonlinear transformations. Linear transformations can be like adding or this y equals ax plus b, right? So you're going to multiply and then add some number, right? That's a linear transformation. For example, converting from Fahrenheit to Celsius. Okay, that is a linear transformation. However, when data is non-linear, you can do non-linear transformations. To achieve linearity, such as log. Maybe we take the log of it. We could do powers, etc. Okay. And so then we can use linear regression. The thing with this is that once you transform it, you got to keep track of your transformations, because once I transform this data, now everything is going to be, my y is going to be in terms of, like, if I transform this with a log, now my y's are log y's, And so then when you go to interpret it, it's now, your weight, it's a log weight, not just regular weight. So that's the only thing you got to be careful of, is kind of tracking those things as you go through this. So looking at this problem here, I just talked about it. Is the linear model appropriate? Probably not, just because we see this pattern here. So no, the data shows / has a clear non-linear pattern. So we need a non-linear approach. The data looks like a power model. So now what we did, if we actually took it, all the length values and cubed them, right? So a cubic function. And so now we can take a look at our output. And so you see how now once we've done this transformation, so here it says here, here's what happens when we take the cube, or when we cube the length values, state the equation in terms of, we're going to state the equation. So here's your output. And this is where it gets a little, like I said, a little weird. So now if I write this, I write weight, and that's my y, is equal to the constant 4.066 plus 0.01467774 times length, but we've cubed all the lengths, so this is to the third power. So to the third power. And remember, when we're doing our predicted, we put a hat on top of our y's. So you get something like this, right? And so now if I plug something in, right, if I want to find the for length 36, I'm going to take a 36, plug it in here. Then I'm going to cube it, and then I'm going to use this equation. Okay. And so that's why I got to be careful, just that once you plug something in, I got to take my length and then cube it before I do anything with this equation. Okay. That's kind of the idea here. Now, same thing here, except here we've transformed the y. So we've done a cube root on the y, and you see we got this. Now, again, a lot more linear than what we had at the beginning. And we have a different output down here. So take a look, see if you can write the equation, see if you can predict. And here's another transformation that we did, a log transformation. And again, same thing, see if you can do the same output. Okay. One last example that I want you guys to look at, and then that's it for these videos. Again, take a look at these. First of all, try to determine, do you think a linear model is going to be appropriate? I'm going to think about it, but you can kind of see here on these first ones. I mean, clearly you have something like this going on, and then here we may have something like this. Okay, so think about what kind of transformations we should be doing, and it's a good chance for you to go on Desmos, type in like y equals log x, type in y equals x to the third, x to the fourth. Take a look at those couple things just to kind of see what those functions look like, and that way you kind of know what kind of transformations to be doing. And so then, yeah, try transform these things and see what happens. See how you do. And yeah, that's it. So that's it for these videos. That's the whole idea of this transformation, is that you can take data, transform it to make it linear, and then we can do our linear inference that we just talked about in the first half of the video. So that's it. If you guys have questions, let me know. We'll go through a lot of the specific details again, like I said in class. But have a great rest of your day.